Okay, ready on your phone. See what's that. Good?
Is it live? Hello, hello. Hello, everyone. I can see some people still getting settled in. So we'll start in a couple of minutes. All right, nice. So welcome to Introduction to Artificial Intelligence with Machine Learning. I know that this might be a really daunting topic, but we'll be going through it at a high school level. So let's get started. Step one is we're going to be installing Python together for our demo. And if you guys have any questions about the process or if you have any issues, make sure to raise your hand and ask Cal here. All right, so for Windows machines, first of all, I want everyone to open up CMD. Does everyone know how to do that? I guess so. All right, so to check if Python's installed, type in python -- version. And if you see something that says like Python 3.10.4, then that means you have Python installed and you don't have to do anything. But if it says something like command not found Python, then go to python.org and download the latest release of Python 3. So this is what their page looks like. Just hover over downloads and click on download for Windows if you're on a Windows machine. And the process is somewhat similar for Macs too. I think I see a couple of Macs. Right. Just with a show of hands, does anyone not have Python right now?
Hi, Trevor.
Hello.
Hi.
All right. I think it won't work on Replit because the library we're using is too big to fit. Do you have Python installed on your machine? Oh. I think I loaned my laptop. Get laptop.
What library are you using? PyTorch? TensorFlow?
PyTorch. Yeah, maybe there's a way to make it work on Replit. All right, yeah, once you get the Python executable installed, you can just run it, and then it should handle the installation for you. The one big thing to make sure you do is to add Python 3 to path. So there should be a checkbox. Make sure that's checked. Okay. Is everyone okay? Everyone on Windows machines?
If anyone has any questions about installing, just raise your hand and I'll help you out.
Yep. All right, let's move on. The next step is you have to check if pip is installed. So just also in the command line, type in pip. If it says something like usage, pip, command, that means you have pip installed. If you don't, then raise your hand and Cal will come help you. Alrighty. I'm assuming everyone on Windows is okay now. Is anyone on a Linux machine? No? Alright, then we can skip that part. And is anyone on Mac and they don't have Python installed or need help? Alrighty. Is everyone ready to move on to the next step? All right, let's move on. Good to go? All right, the next step is we're going to be installing PyTorch, which is our machine learning library that we'll be using for our demo. So this part's really easy, just using pip or pip3, depending on the name of your pip executable. Type in pip install torch, then Torch Vision, and OpenCV-Python. Those are the 3 libraries we'll be using. The big one's Torch. That's the one that does the machine learning. Is anybody having issues? CV. All right, is anyone still having any troubles? Is Python PyTorch installing? All right. If you have any more issues, just raise your hand and Cal will come help you. While we're waiting for PyTorch to install, let's get started with the main course of this workshop. All right. So let's talk about what is artificial intelligence. Well, the first concept that we're going to learn is that computers are dumb. And this is probably what you've seen in a lot of your introductory programming courses, is that computers need very specific instructions to do things, right? So let's talk about what computers can do and what they can't do. We all know what they can do. They can add 2 numbers, add 2,000 numbers, or like draw a rectangle. Something like that, right? Now, what can't computers do? Well, they can't peel a banana. They can't play Super Mario World. They can't drive cars. They can't draw pictures, compose music, recognize that that's a cat, recognize that that's a dog, or understand English. So, wait. Okay, so computers can peel a banana, They can't play Super Mario World, they can't drive cars, draw pictures, compose music, recognize that that's a cat or a dog, or understand English, right? That's a meaty file. Those are some cats, some dogs, and this one's actually really cool. What the computer does is it takes an input sentence, so a painting of a fox sitting in a field as sunrise in the south of net, and then it outputs an image. So basically the computer can understand English. Anyways, what I just said was all wrong. That was a lie. Computers can do all of this. All right, and why can they do that? It's because of research into artificial intelligence. Yep. So what is the definition for artificial intelligence? I just shamelessly ripped this definition from Britannica, but basically what it says is artificial intelligence, or AI, is the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings, so like humans. And a popular method of achieving intelligent behavior is using artificial neural networks, or ANNs. And lots of research has been done into ANNs since even the 60s, before computers were a big thing. What they do is that they mimic biological neural networks, so like our brains. And we'll take a look at a visual model. So this is a neural network. It's probably what you're used to seeing in those machine learning videos. And its formal name is a multi-layer perceptron. We'll be focusing on this type of ANN in this workshop, but there's a bunch of different types. This is the most commonly first taught. So let's discuss some terminology. The circles over there are called neurons. If you look at the arrows, the inputs into a neuron is called a dendrite, and the output from the neurons is called an axon. And now you might notice that it's an analog to real-life neurons. So as you can see, there are dendrites, axons, and the cell body is the neuron. Right. In an artificial neural network, neurons store numbers. And what axons do is they take a number from their neuron that they're attached to, transform it somehow, and then pass it to the dendrite of the next node. So for example, that axon over there would take the numbers of this neuron, change it a bit, and then pass it here, that output node. And yeah, neurons are also called nodes, and dendrites and axons are called connections. So sort of like graphs. We'll be taking a look at a simple case first. So this is a perceptron. What we saw here was a multi-layer perceptron. This is just a perceptron. And I'll explain the weird box in a bit. So a bit more terminology. The blue ones are called input nodes. So they take an input number and they pass it to the network. The green arrows are called connections. The red circle is called the output node, because that's where we get our output. It stores the output number. And we have like the X and Y, sort of like the graphs we have in math. And the W is called a weight. And with the biological naming scheme, it's also called a synapse. And the box is called an activation function. And we'll talk about what that means in a bit. Let's go through how the perceptron takes an input and transforms it to an output. So we have our input nodes that take x1 and x2, which are just two numbers. Let's go through the top half first before we tackle the bottom half. And W1 and W2 are also just numbers. Those are the weights. So what we do is we take the input x1 and we multiply it by the weight W1. You get that term, and then We'll just leave it here right before the activation function for now. And let's take a look at the bottom half. We take x2, we multiply it by the weight w2, and then we pass it to the activation function. And then with those two terms, once we've computed all the weight multiplied by the inputs, we just add them. And after we add them, we pass them to the activation function. And is everyone here familiar with function notation? You usually learn this in, I think, functions, grade 11 math. Is everything okay with it? Everyone okay? Here, I'm going to make a chalkboard demonstration. Right, and that symbol is called sigma. Sigma mill.
Good one.
All right, so a function, we have our function sigma. I'll write that here. And then as the parentheses, and inside there's a number, so like 2. And what the function does is it takes the input number, then does some sort of transformation on it. So let's say we have a function f. F takes an input x, and then it returns an output x plus 1. So it's sort of like programming functions, except in math notation. So we have this function called sigma, and into sigma we pass our weighted sum of the weights multiplied by the inputs, and then that's the value for y, so the output node. Is everyone okay with that? Awesome. So this is our big equation here. It's y is equal to the activation function sigma multiplied by the weight of the first node multiplied by the inputs of the first node plus the weight of the second node multiplied by the input of the second node. And usually when people are drawing diagrams in neural networks, they just imply that the activation function is there. So they combine sigma with 1 into that. Just so it's easier. It's a hassle if we have to write sigma every single time. All right, sigma. What is sigma? Well, it can be, activation functions can be any function really. And in our case, we're talking about the Sigmoid function. So this is what it looks like. It takes a number x and squishifies it between 0 and 1. As you can see from our graph, where the x-axis is x and the y-axis is sigma of x. And the reason why we want to do this is because of nonlinearity. I can see it's like curvy, right, instead of being linear. And why do we even want nonlinearity, right? So imagine if we didn't take the activation function, or sigma, of the weighted sum. Now the first part should look a bit familiar from grade 9 math, right? It's like y equals mx or y equals mx plus b. So what this actually is a linear function. And if you take the x2 term as well, that's the equation of the plane. And we can't really get into the deep details, but think of nonlinear functions as being way more flexible than linear functions. So for example, if we wanted to divide two sets of x's and o's, then with a linear function, it'd be pretty hard with this distribution, right? But with a nonlinear function, it's pretty easy. Just go like loop around. So we want our sigmoid function for nonlinearity. And the sigmoid function isn't the only activation function out there. The one we'll be using for our demo is called ReLU, and it's one of the more popular ones nowadays. There's another one called the tan-h, and it can even just be any function. So like f, or question mark, question mark, question mark. So yeah, we use sigma for now, but sigma is easier to write than ReLU or tan-h. More generally, a single layer perceptron or just a perceptron can have more than 2 inputs. They can have, let's say, n inputs. And they all go to the activation function, they all get added up, all the inputs get multiplied by their weight, and then they get added up, and then the activation function gets applied, and it gets passed to y. And in code, we usually pass it to the neural network in the form of an array of inputs. Everyone okay so far? Sick. So finally, combining perceptrons with the same inputs. So say we had 3 perceptrons that all took the same inputs, x1 and x2. And they want to have 3 different outputs, y1, y2, and y3. And they all have different weights. So we had W11, W12 for the first perceptron, W21, W22 for the second perceptron, and W31 and W32 for the third perceptron. Well, we can combine them into this. They're starting to look more like our multi-layer perceptron that we saw at the beginning. And as you can see, each of these perceptron outputs, or the nodes in the output layer, have their own function, have their own equation. So sigma multiplied by the weighted sum. And in ML lingo, the nodes are called layers. So these ones are like stacked vertically. This is one layer of nodes. This is an input layer of nodes. So it's another layer of nodes. And in between, there's a layer of weights. All right, and here is a multi-layer perceptron with 2 layers instead of 1 layer. And what this one does is it pretty much stacks another perceptron on top, taking the outputs y1, y2, y3 as the input. So there's 2 layers. There's our first layer of weights. There's our second layer of weights. And as you see, there's an input layer on the left, an output layer on the very right. And in the middle, in between the input and output layers, people like to call them hidden layers because they're sort of hidden inside the neural network. So stacking layers into deep neural nets is how we get complex behavior and how people drive cars with neural networks. Right, so why do we care about neural networks, right? Well, an interesting fact that was proved some time ago, I think probably in the 60s, was this right here in italics. Given the right set of weights, a neural network with one hidden layer of nodes can fully approximate almost any function. And the way we achieve AI is that we find the right set of weights for a neural network so that it performs intelligent behavior. And machine learning with respect to ANNs is just teaching an ANN how to perform a task by tuning its weights. We do this by giving the neural network an example input and seeing how wrong it is, and then we can determine if each weight needs to be increased or decreased. So it's sort of like an iterative process. And we'll be going through an example right now. Is everyone okay with it? We'll be using the MNIST datasets. And what the MNIST dataset is it's just a collection of images that a bunch of scientists gathered together. They're 28 by 28 images of handwritten digits, and they're all labeled. So what labeling means is you have an input. So for example, this 5, and then there's some data attached to it saying that, oh yeah, that's a 5. And we can use that for training. So let's figure out our neural network's architecture first. So what is our neural network going to look like? Well, our data was given to us as 28 by 28 grayscale images. And grayscale just means that it's black and white. Grayscale images are stored as 2D arrays of numbers. So usually from 0 to 255, that's a standard. But sometimes people represent them between like 0 to 1 or any arbitrary range. Black is 0, white is 255, and gray is any number in between black and white. And as you can see, each pixel is just a number representing its part inside. We can flatten the 28 by 28 2D array into a 1D array of 784 inputs, because 28 multiplied by 28 is 784. And the way we flatten a 2D array is that we take each row one by one, and then we sort of concatenate them together into a 1D array. And our output format, our task is called a multi-class classification task. which means that we want to output an array of 10 probabilities. And each probability is just how likely the neural network thinks that this is the right number. So for example, P0 is the probability that the input digit is 0. And P4 is the probability that the input digit is 4. And this is what the neural network thinks. So it might not be right. The neural network might be completely wrong and think that, let's say, a 5 is actually a 9. Right. So we have our inputs and outputs defined. We want an input layer of 784 nodes, an output layer of 10 nodes, and we'll have a hidden layer in between. We'll go through that during the demo. So step 1 of the training process is called data preparation. So the way we train neural networks is by preparing data, right? So solved examples for the neural network to learn from. We prepare the examples that we showed to the neural network, and this process involves downloading the MNIST labeled images, flattening the images into 1D input arrays, and associating each input array with a label. So something like this. We have the image of the number 3, and it's labeled as 3. And then we just simply flatten that into a 784 length array, and we keep in the label that says that that is 3. And we do this for every single example. Usually datasets are pretty big, so they might contain millions or hundreds of millions of examples. Now here's our model architecture that we'll be using for the example for the demo. We'll have 2 hidden layers in between the input and the output layer. And the hidden layers will have 128 nodes and 64 nodes. And in between each input layer and in between each layer of nodes, there's an amount of weights. And the number of weights is just the number of nodes in the input layer and multiplied by the number of nodes in the output layer. So like if you're going from hidden layer 1 to hidden layer 2, there'd be 128 multiplied by 64 nodes. Yep. Yeah, a lot of like this setup comes down to trial and error. There are some guidelines, so you don't want them to be too big to have too many nodes, and you don't want them to be too small, or else it can be, right? Yeah, but for now, let's just say that these are numbers we want to use. I tested them before at home, and they work pretty good. Yeah, like scientists do write entire papers, like testing different model architectures and comparing their results. So this is where a neural network is going to look like. Obviously, the number of nodes isn't right. Like the first layer of nodes isn't 784 nodes. The second layer isn't 128, and the third layer isn't 16. But those can't fit on the slideshow, so let's just say that this is what our model looks like. And it outputs 10 probabilities. And now, in one training iteration, we want to do something called a forward pass. And a forward pass is just what we did with the subtron. So we pass in the inputs and we get the output. All right, so we get our input array, and then it goes through the neural network and then gets outputted as an array of probabilities, our 10 output nodes. And then what we want to do is calculate the loss. And what the loss means is it's just a measure of how wrong your model was. It's a measurement of wrongness. And this is just a number, and the bigger the number, the more wrong your model was. A loss function compares the output with the label to see how wrong, to get the loss, to see how wrong the model is. The further the output is from the label, then the greater the loss. So let's say if your model thought that there was a 50% chance of an input number being equal to the number 3, and the number was actually 3, well, the loss would be lower than if the model thought that the probability was like 25%. So it's just a measure of wrongness. And doing multi-class classification, so classifying inputs into 2 classes, we use a loss function called cross-entropy loss. And that is a mouthful. You don't have to worry about what it does. All you have to know is that it compares the output array y with the label. And then it spits out a loss value. Right. And now let's go back a bit. We know that by changing the weights of our neural network, then we can change what the output looks like. Which means that if we adjust the weight values and change the output, the loss value will also change. For example, if we have a weight called W12, if we change it, it will impact what the value of the loss is. And thus, the loss is a dependent variable, and W12 is an independent variable. And we can graph this. So we have our loss graph with respect to W12. And here we have a point on the graph. Let's say that that's the current loss for the current value of W12. Let's take a closer look at it. Should we increase or decrease W12 to decrease the loss? Increase? That's right. And we can tell pretty easily visually, right? Because if we move W12 to the right, then the graph goes down. And machine learning pretty much just comes down to minimizing the loss function. There we go. Computers do this computationally, so they decide on whether each weight needs to be increased or decreased using the backpropagation algorithm. It essentially just does what we just did, except for every single weight. And it's a bit math heavy, so we'll skip the details for this step, but luckily for us, PyTorch handles it all for us, so we don't actually have to know the math. And then finally, at the end of the training step, we apply an optimizer step. So once the computer determines which weights it needs to increase and decrease, the optimizer slightly adjusts the weights accordingly. And now the loss is slightly decreased. And then we rinse and repeat, give this a couple thousand, couple million times, and we have a trained model. And the name of the algorithm we just described was called gradient descent. And it's called gradient descent because you look at the gradient of the graph, and then you look for the winner spot, or the lowest cost. The place on the graph with the lowest cost. So let's implement all the theory we just learned on PyTorch. I'll be switching tabs onto, first of all, I want everyone to go onto this GitHub repo, and I have some testing code I can use to test the model that we'll be training. Alrighty. So let's take a look at this repository here. All right, we have this open. I want everyone to open testtool.py. Don't worry about main.py. And just copy and paste all the code. All good? All right. Now in your favorite text editor or IDE, open up a new folder. I called mine GemHacks demo here. And just leave it empty now. All right, and we'll just be copying test tool into this folder. So test underscore tool dot py. Typing with one hand's a bit difficult. I'll clip on my mic onto my collar. Awesome. So yeah, just copy and paste that in. Is everyone good to go for that? All right. So we'll make another new file called main.py. Main.py. And we'll be doing an import test to see that all of our libraries are good. So first type import torch. Import torch.nn as nn. And from torch vision, import datasets and transforms. And then to check if all of our libraries are installed correctly, just try running main.py. If it doesn't complain about anything, then that means we're good. And once again, if you guys have any issues with libraries or installations, just raise your hand and Khaled or I will come help. Is everyone good to go? Got all the imports? All right, we'll wait a bit. Yeah, sure. So Torch is PyTorch, as we explained earlier. That's our machine learning library. Torch.nn is a part of PyTorch that we use to construct our neural networks in code. And Torch Vision is what we use for our data set and to apply any transformations to our data that we might need to do. All good? All right, I think we're ready to move on. So, first thing we're going to do is make a skeleton for our train function. So we'll define a function called train. It'll take in the arguments model train underscore loader, our loss function, and the optimizer. And we'll go through what train loader means in a bit. And we'll just type pass here because we'll skip this part for now. All right, and here's our main function. So def main, it'll take an input called n epochs. Actually, that should be all caps. N epochs. And what an epoch is it's just like one complete step of training. It's when your model has been trained on every single piece of data in your data set. So we have our main function defined. Let's write some setup code. First of all, we'll be making our transforms object from Torch Vision transforms. So let's just call it a variable called transform. So we'll do transforms.compose. And what the transform.compose does is it just attaches together a bunch of transformations that we need to do to our data for a setup. The first one is, it's an array, and the first one is transforms.toTensor, and the second one is transforms.normalize 0.5, 0.5. And tensor is probably a word that you guys seen thrown around. What it just is it's a generalization of 1D arrays, 2D arrays, and 3D arrays. So 1D array is a 1D tensor, a 2D array is a 2D tensor, and a 3D array is a 3D tensor, and so on. We don't really have to worry about using messing around with like 3D arrays or like 4D arrays. All right. Everyone okay with transforms? Yeah, that might help. That looks better. And the normalize, it takes two numbers, 0.5, 0.5. What normalize does is essentially makes sure that the range of each of our numbers in our input is between roughly 0 and 1. If you guys want more details on the code, just you guys can just ping me on Discord or approach me after the workshop, because we are a bit tight on time. Anyways, I think everyone's okay. Next thing we'll do is we'll set up our train loader. And the train loader is just a quality of life feature that PyTorch has. And it helps us load our data like really nicely. We can loop through all of our data in a for loop. It clusters our data together into batches. I'll go through what batches means. And yeah, it's pretty nice. So we have train loader is equal to torch.utils.data.data loader. And the arguments is train data, train data, and the batch size is equal to 64. And I missed a step. Here we go. This is what train data is. Train data is datasets.mnist. And then here's the directory that we'll download the data into. Download equals true sets it so that PyTorch will automatically download the data for us if we don't have it. And then we have train is equal to true because this is our training data set. And the transform is equal to the transform object that we just made. And I'll give you guys a second to type that all out. All right. So we have all of our data packed into our train loader, which will then pass to our train function in a bit. But now let's set up our actual neural network. So let's call it model, a variable called model, and it'll be nn.sequential. And then, all right, press enter, and we pass it a list of components that we want our neural network to have. And just what nn.sequential is, it's sort of another quality of life feature that PyTorch has. It makes it super easy to set up a neural network, but it's not usually what people use in like industry, since there's not as much control. But for our purposes, this is fine. So the first component we'll have is nn.linear, and the arguments is 784 and 128. And it's just a linear layer. And what a linear layer is just the weights layers that we've been seeing in multilayer perceptrons. So they call it a linear layer. All right. And the first number is the number of input nodes. the second number is the number of output nodes. So we go from 784 to 128. Then after this, I should add a comma. We type nn dot ReLU. So yeah, in machine learning libraries, they actually separate the activation function from the layers just to give people more control over which activation function you want to use. We'll be using ReLU because right now that's like the best one or the most popular one that people use right now. And now we'll just make the rest of our network. So we'll have another linear layer. It'll go from 128 nodes to 64 nodes. Another ReLU layer. And then we'll have a final linear layer that goes from the second hidden layer to the output. It'll go from 64 to 10. And yeah, that 10 is just our 10 output nodes of the probabilities. Yep. So an optimization that people do when they're training their models is instead of going through one input array at a time, they like to batch them together, and they use some tensor map techniques. So like with 2D arrays to make it sort of go faster. We don't have to worry about it for now. Just think of it as we're passing in 64 numbers at a time, and it does it all at the same time. 64 inputs, not numbers. Anyone else have any concerns? All right, so we have our neural network, we have our data. Let's get our loss function. So loss underscore function is equal to nn dot cross entropy loss. Perfect, and then we have our optimizer. Optimizer is equal to torch dot optim dot SGD in all caps. And then what SGD is it stands for stochastic gradient descent. Don't worry about what stochastic means, but it's basically just an approximation of full gradient descent. And then we pass it the parameters of our models. So parameters is another way to say just weights. So we pass it our model weights with the parameters function, and then we give it LR. And LR just stands for learning rate. The bigger the learning, the bigger the steps that the optimizer takes. Alrighty, and now we can get to our main training loop. We do a for loop, so for epoch in range n, say 1 to n epochs plus 1. And we just do the 1 to n epochs plus 1 because of the whole indexing thing. So this goes from 1 to the number of epochs. We have here is, here we do our training function. So we call the train function, we pass the model, the train loader, our loss function, and we pass it the optimizer. And eventually we're going to code our train function so that it returns a loss value for us, just so that we can get some diagnostics. So let's call it train loss equal that. And now let's actually move on to coding the train function before we finish the training loop. Alrighty. The first thing to do when we're applying a training step is to type model.train. It doesn't do anything for us right now, but eventually when we add like some dropout layers or other optimizations that only apply for training and not for actual model usage, this will come in handy. So we'll write it out right now, just so that we get used to it. We'll have a variable called total loss equal to 0, and this will just be a running count of our loss so that we can get the average later. We got a for loop, for images, labels in train loader. Oops. Yeah, so like I said before, the nice thing about train loader is that it bundles together the input data, so images, with its labels, and then lets us for loop over it, like that. Then in the body of the for loop, first we get the batch size, equal to images.shape. And I should probably go over what dot shape means. I'll type it out. So right now what images looks like is, like we talked before about batching, it's a batch of 64 images. And the images are 1D arrays. And the way people decide to represent this is with a 2D array of a bunch of images, input arrays. Just like 0, 0, 0, 1. We have 1, 2, 3, 4. Oops. 1, 1, 1, 1, and yeah. So this is a 2D tensor using our new terminology. And the shape of this tensor is just the length of the, like the width and the length. So the shape would be an array. The first value is along the first dimension, so it's down. Or yeah. This is what the shape would look like. It'd be of length 3 and width 4. So there's 3 1D arrays, and each 1D array has 4 values. So this is why our shape looks like 3 and 4. Right, so to get the batch size, we just take the first number from the shape. And we can delete this part. And then right now, what our data looks like is the images are actually 2D arrays, and we have to flatten them. And that's really simple. We just use image is equal to images.view batch size 784. And this resizes our images tensor. I guess I can give a better explanation after the workshop. Let's get moving though, because we still have the trainer model. Anyways, so those 2 lines just format our input data so that our model can actually read it. So next step is, first, we type in optimizer.0grad. That should be 0. Optimizer.0grad, and what that does is it clears all the gradients from the model weights. Basically, it just resets the optimizer. And we have to do this every time, or else like training from previous loops will get into this iteration. And then we get the output from our model. To pass the input array, it's really easy. We just treat the model like a function, and we give it the array of images. And then once we get our output array, we can compute the loss with our loss function, which is cross-entropy loss. So we have output labels. Just like on the slideshow, the cross-entropy loss takes the output and compares it with the label and spits out the loss. And this is the really nice part about PyTorch. To do backpropagation, we just type in loss.backward. And it does all of it for us, which is pretty awesome, in my opinion. Once the computer has computed all of the gradients and figured out which direction the weights need to move, then we can tell the optimizer to step the weights, to perform a step, so to tune the weights a bit. And now we finished one training iteration. And what we'll do after is add to the total loss the loss we've computed. Dot item. So dot item so the output of the loss function is a tensor with one number. So we just use dot item to get the number out of that tensor. So we add the loss to the total loss. And then at the end of the for loop, after we've iterated through every single example in the training data set, we compute the average loss. So average loss is equal to total loss divided by the length of the train loader. And then we just return average loss. Everyone got it? Let's move on. We'll go back to our training loop here. And now let's make some print statements. So our train function returns the average loss from the training, the entire step. And then we can just print that out. So we'll print out first the epoch number. So this print epoch plus stringify epoch. Then below that, we'll print the loss. So loss, and then we give it the stringified version of train loss. And then for every fifth epoch, we'll be saving our model onto into our folder. So if epoch %, so modulo 5 is equal to 0, then we torch.save model.stateDict. And here's our file name. We'll call it mnist.nn.pt. And the stateDict of the model is just where it stores all of its weights. They called it a stateDict for some reason. So we give that to the torch.save function, and then let's print out a log. So saved model to mnist.nn.pt, not py, pt. And finally, we just call the main function. So let's train it for 20 epochs. So we'll just pass 20 to main. And our code should be ready to go. Yep. 133. Maybe I made a typo. See this? There should be an S there. Maybe just try running main.py and see if it still has the error. Anyways, yeah. So to run our training script, we type in Python or Python 3, depending on the name of your Python program, then main.py. And then what we'll start doing right now is it'll download the MNIST dataset into a folder called data. Is it working? So is everyone's model turning right now? It should be printing out like the block and once. All right. Once your model's finished training, so at the end of epoch 20, then you can play around with it with the test tool I wrote. I want to look at this also, there's no GUI, but just type in Python or Python 3 test underscore tool dot py. And it should pop up a small window. You can draw in a handwritten digit. It'll use the model you trained. I'll be posting my version of main.py onto the, you guys want, onto the Discord. No worries. All right, so we're a bit over time. I'll get to the end card right here. Oops, that's the wrong tab. Hold on, I've closed it. It's fine. All right, so there's the slide for testtool.py. All right, thanks for listening, guys. AI is pretty cool. This workshop actually barely even scratches the surface of the world of artificial intelligence. So there's our iceberg, and we're at the very tip over there. If you guys are still curious about machine learning and neural networks, just reach me at due2 hashtag 4483 on Discord, or I'll be hanging around for today. All right, and that's the end of the workshop.
Then just quickly studio or run Backpropagation.
All right, bye guys.